Customers of Cellulose Helicopter Company have been complaining about the limited flight time of their helicopters. So we need to study how the basic design might be modified to increase flight time. During this investigation, we'll put into practice a 2 to the 8-4 fractional factorial design, the design we've discussed before, and use normal plots and the cube plot to analyze the results. You'll see how fractional factorial designs are useful in screening large numbers of factors during the early stages of investigation. We need to find out which factors are important. At this stage, we're looking for large effects, separating the vital few from the trivial many. With a screening design, we can do that with only a small number of runs. Remember that factors which are found to be important during this screening stage can be studied in more detail later if that turns out to be necessary. As a first step, the Cellulose Helicopter Company forms a team. The team includes a design engineer, a manufacturing engineer, a pilot, a field representative, and a manager. A long brainstorming session ensues, during which the team members compile a long list of possible factors that might affect the helicopter's flight time. A great many possibilities are suggested: body weight, weight of the paper, body dimensions, wing length, wing shape, and so on. And after much discussion, the list is finally narrowed down to 8 factors. Here's a paper helicopter. The 8 factors they finally decided on were paper type, wing length, body width, whether you put a paper clip on the thing, whether you fold the thing here, whether you tape the body, whether you tape the wing. To run a full factorial experiment with 8 factors, we'd have to build 2 to the 8th. That's 256 different prototype helicopters. Instead, we're going to use only 16 prototypes to screen the 8 candidate factors, and money saved at this stage can be used for later studies. As a general rule, not more than 25% of our resources should be used in an initial experiment of this kind.
The most useful designs for prototype testing and engineering use are the 8-run and 16-run two-level factorial designs. We've collected these in this table called a practical aid for experimenters, and this provides you with all these designs. If you turn to page number 1, you will find the table of contents and a directory of all the designs. So for our helicopter experiment, we have 16 runs and we have 8 factors. So we go in here on the line that says 16 runs and go to the column that says 8 factors, and there you find that it says go to page 29. So then if we turn to page number 29 of the table, you'll find a design template that looks like this. Here is the design matrix with all the pluses and minuses, and then there's a column, blank column here for writing in the responses, and a blank column for writing in the random order. At the top, for good record keeping, we have made a line here for naming the experiment, your name, and the date of the experiment. Now this is a resolution 4 design, and you can see that up here it says 2 to the 8-4. That subscript here indicates the resolution. And resolution means that second-order effects are confounded with other second-order effects. And you can see that down here at the confounding pattern at the bottom here, that second-order effects are confounded with other second-order effects, and that means it's resolution 4 design. In fact, also the main effects are confounded with third-order interaction effect, but we have left them out because they are usually small, and so we have ignored them here.
Another way of getting this design is to use a computer and experimental design software, such as SCAs. To determine the appropriate design, all I have to do is enter the number of runs desired and the number of factors we have, and the software will print out the design together with the confounding pattern automatically.
With this design, we now assign the 8 factors to the columns. So as we've already done here, you see paper type, wing length, and so forth, and also the name of the response, the flight time.
You do the same thing using a computer. You just name and enter the factors.
We also need to randomize the run order. One simple way to do this is to cut out 16 pieces of paper with the numbers 1 to 16, and then mix them up and draw out the numbers and write them into the random order column. So for example, we'll draw out a ticket here, and this one has 7 on it, and we'll write that up here.
course, the computer will randomize automatically.
The next thing we need to do is to build 16 helicopters according to each line in this design. We've already done that, so we have 16 helicopters built. And so, for example, if we take the one that is random order number 1, which is standard order number 5, that is this helicopter here, number 5 on, and you can see it says here paper type is minus, so that is regular, and wing length is minus, so that means short wings, and it says body length should be plus, so that means the body should be long, and so on.
So, okay, now we're ready to run the experiment.
So here are the results from the 16-run experiment here, the 16 flight times. I provided a means of manually calculating the effects of the various factors in the practical aid for experimenters.
If you have a computer, you just enter the results, and then the computer will calculate and print out the main effects and interactions automatically.
In order to see which effects are important, we plot them on normal probability paper. In the back of the practical aid, we've provided pre-printed grids so that you can make these normal plots very easily.
The computer also generates a normal plot. Now, using a computer with statistical software really makes exploratory data analysis very easy, because cube plots and normal plots and all of the arithmetic involved is done very simply and very quickly.
As you can see, I've just completed now the normal plot. In the middle, we have the trivial many effects. And then we see one large effect out here, which is the wing length, and one large effect, which is the body length down here. So therefore, wing length is the most important factor for determining the flight time, and to some lesser degree, the body length.
With this 1/16th fraction design, we've isolated two important factors. To see what they do, we can plot the data for these two factors on the corners of a square. Equally important, however, the square suggests a direction for further modification of the helicopter design. So now we see which way we should be going. The question is what further experiments might be run in that direction. And in the next tape we'll talk about this. We'll talk about sequential assembly of designs, building designs in modules, so that each experiment is adapted from knowledge that's gained in the previous experiment. And you can see why it's important to spend not too large a proportion of your total resources on the initial experiment. In this case, the experiment showed that even better flight times could be found outside the region of the first experimental design. In practice, early experiments sometimes change the whole direction of investigation. Thus, initial experiments might show a different performance characteristic, such as flight stability, was overwhelmingly important and might dominate the future investigation. Always remember the process of discovery is iterative. The results of each stage of investigation generating new questions to be answered during the next.